Hi, my name is Albert Dunford, and in this tutorial video we are going to look at digital control, the effects of delay in a digital control system, and what happens when you design an S domain controller and try and convert it into the digital domain without giving any thought to the effects of digital delay. So let's run this simulation. We have a stable PI controller on the current on the left, and we've added in the same PI controller on the right, but now with digital delay, and let's see what happens. So here we can see the analog domain current and the analog domain voltage, both looking pretty stable. Let's add in the current to the for the digital controller up top here, and right away we see that we've got some problems, and I'll add in the voltage here at the bottom just so we can have a look at that as well. But here we can see that our current is not continuous. It's oscillatory in nature. The controller really is not working very well at all, and that's because of the delay effect. So what we need to do in order to digitize this controller is we need to redo the AC sweep, or the frequency response of the plant, with the digital delay accounted for. So we'll do that now. Okay, so here's the open loop response in the analog domain, and I've got my same perturbation coming in, and we'll look at the response here in the digital domain. So we've got our zero to hold modeled, and we've got our unit delay modeled here. So we should just be able to run the simulation and look to see what the digital transfer function looks like. Here's my parameters for my AC sweep. We're going to go from 100 to 85K and look at 60 frequency points along the way. And let's run the simulation. So here's the simulation results. We've got the amplitude on the top here, so we can see the difference between the S domain controller and the Z domain controller is, or response, open loop response is the same. On the bottom here we see that at lower frequencies everything looks pretty good, but then as we start going up in frequency the phase really falls off, which is why that original controller that was in the S domain was okay, but in the Z domain it's not okay. So that's what is going on here. So let's take the digital response and import that into SmartCtrl and do a design for a digital controller. Okay, I'm going to import my frequency response into SmartCtrl. Again, we'll go up to the Create New Document and Launch Initial Dialog. We'll import a frequency response down here. Current mode control is this one. We'll browse the file. It is the current digital one here that I resaved as. You can see here the same response with that phase rolling off there. Switching speed is 250K, and the current set point is 0.782. Hit OK. Popped up on my other monitor. We will do a current sensor. We'll give it a gain of 1, and compensator will go for a PI. And then remember 1 and 0, so a sawtooth waveform. These are the parameters I want, so an on time of 3.96 microseconds, and then a peak of 1 volt and a valley of 0. So we'll hit OK. And then let's just hit a point here and get to the design screen. Again, with SmartCtrl, this reference step solution here uses frequencies that we have not imported, so we should use this with caution. I like to do my design with these three curves here, so pink being the controlled output, green being the plant, and brown being the closed loop response, and also the polo plot here. So we can move this operating point around and try and find a good looking solution. And then what we can do then is import that back, the parameters back into PSIM, and go from there. Okay, so I've got my coefficients determined now. These are the design point that I've come up with. Is right here, so 12K on the cross frequency and about 60 degrees is the phase margin. These are what the plots look like. So if we come back here, I've imported these into PSIM. So we've got our coefficients here, 309 milli and 91 micro. That's what this PI block has. So this is a digital PI block, you see that it comes with a sampling frequency down here. So we can now run this simulation and we should be able to look at our current loop response, and we can see we're looking pretty good there, and we're also can pull up our voltage. Okay, so those are those plots. We'll use this now in a new video to close an outer voltage loop, and so check back again soon for that one. I'd also like to mention at this time that you could use the S to Z converter tool up here to convert the time constants here. So 309 milli, let me just readjust that. So we could do it in here as 309.581 milli, and then the time constant here would be 91.55 micro. And if we set up a 250K as the frequency here and we converted this, we could implement a PI controller with this setup here. So this is the bilinear equivalent, the backwards Euler equivalent. The digital PI block that we have here, if we go in and read, this is being implemented with backwards Euler. So the equivalent would be, if back in the S to Z converter, would be backwards Euler, would be this one. So we've implemented this with this block. Okay, so that's that for this tutorial video. As I said again, we'll use this to close the loop. And so check back soon for more tutorial videos. Thanks so much for watching. Bye now.